Yeah. Okay, let's get started. Oh, it's really loud. Okay. Hello. Okay. Yeah. This time we talk about our the core part of the factoring algorithm, which is this order finding algorithm. Okay. And so we need to do this order finding problem, which is a very mathematical problem. We're given two natural number x and n, with x less than n and x and n are co-prime to each other, and we to find this order of x with respect to n, which is you keep multiplying x with itself, and when this equal to 1 mother. Okay? And here we have an easy example: x equals 3, n equals 7, and we can keep multiplying this 3, and we see that we multiply 6 times it back to this 1 mod 7, and so if you multiply 7 times, you will get back to this 3 mod. And then we see that we can do this by period finding. By using the phase estimation on this oracle, this multiplication oracle ux. Okay? And we define this multiplication oracle ux of y equal to x times y mod. Okay? So this x is this x here. So x on some y, it will multiply by x. Okay? And then we see that if you think about what are some of the eigenvectors of this ux? Ux actually, so ux is n by n matrix, so there will be n eigenvalue and n eigenvectors, but we actually only care about the eigenvalue and the eigenvector with associated with y, basically y equal to x. Okay, and we know you keep multiplying x by itself, it will get this orbital from x to x squared all the way to x to the r, so there will be r different things, and we only care about those r different eigenvalue and eigenvectors. We see that we take an equal superposition of those states, it will become eigenvector to our ux with eigenvalue 1, because you the ux on it just shift all those x power, so 1 power 1 become power 2 become power 3, etc. And so ux on this thing, you just cyclic shift all those components here and get back to the same state, still u, and this state is called u0, but we can get some eigenvectors that look like this, but with non-trivial eigenvalue. That is, you add some omega to some power in front of all those x, so you can add omega to the so if we say omega 1, 2, 3 powers in front of it, and you see that you add ux on it, okay, with and here omega is the negative as root of 1. Okay, omega is e to the 2 pi divided by r, and then you add ux on it, you see that on this u1, you see that you get eigenvalue omega minus 1, because you shift everything, you increase the power of x by 1 on everything here, so then that's equivalent to you decrease the power of omega by 1 here. Okay. And similarly, you can have u2, etc. And if you write down everything in algebraic expression, then us is this omega to the sk, so this thing is just omega to the s times k, and times x to the k mother, and sum over ok, k from 0 to r minus 1, and some normalization. Yeah, so this part is just this big exponential is omega to the sk, and you can do this check with more algebra, and you see that indeed you apply ux on this us, you get omega to the s as eigenvalue. Okay. And so now we see those eigenvector and eigenvalue. We see that we do phase estimation work on this eigenvector, we should get this eigenvalue s over r. Okay, and but we don't have this eigenvector, so we give the superposition of those eigenvectors as 1. 1 is actually the equal superposition of all the eigenvector, and so if you do phase estimation, we'll get the random S over R. Okay. And yeah, that's the idea. You get random S over R, and you get a whole bunch of those. You can get R. Okay. And so that's the yeah, that's the idea of the algorithm. Okay. And so we said that there are a whole bunch of tricky points for doing this. Okay. And so first one is this UX is actually not so easy to do, especially that when you need to do it on very high power. Okay, and for the very high power, we can do this by repeating squaring. And there's another tricky point is well, this multiplication itself is also tricky because it is in place multiplication. Okay. And to deal with that, it's actually not too hard, but I think it's easier to just give you as a homework. Okay, so this is one of the book problems, and it says that you can actually do this with addition oracle instead of this multiplication oracle. So we'll just add the power of x onto another register, and I guess a bit of a spoiler. So after you, where do we apply the oracle? Okay. After we apply the oracle, the state here you get here is actually, so you have a j on first register and x to a j on second register. Okay, so instead of thinking about you doing multiplication oracle, you can just think about you initiate first register as the sum over j and second register as 0, and you just use the addition oracle to add x to a j to the second register, so you get this state. Okay. So that's a bit of hint to your homework. Okay. So yeah, think about a different way to get this state here. Okay, this state, you can use the addition oracle to get this, and the addition oracle are a bit easier to construct. Okay, that's the first tricky point, and then there is a second tricky point. Is you get some S over R. How do you yeah, you get some S over R with some precision. How you some approximate of X over R, then how do you actually get your S and R? And I've seen that you can do this with the continuous fraction algorithm, and it's something like this. So you just keep flipping the fraction here, and you cut off at some point, you will get S and R that's not too big. Okay. And yeah, so that's the continuous fraction. And lastly, we have that S and R might not be coprime. So even if you get this S over R as a nice number, you may not get your true R. Say that your R equal to 6 and S equal to 2. And so your S over R is 1 over 3, but you don't know it's 1 over 3 or 2 over 6, etc. Okay, and we say that we can do this by just finding multiple Si over Ri. And so all those are coprime to each other, and but we find the least common multiplier of those Ri. We have a high probability of finding the HOR. Okay, and yeah, let's go through the number theory a little bit here. The number theory is that well, we find okay, so here we have a whole bunch of notation. So before we get rid of the common factor, let's call it S1 prime and over R, and the S2 prime over R, etc. So the S1 prime and S2 prime are like the HOS, and R is the HOR. But then you get out of the common factors, so we have S1 over R1, S2 over R2, etc. And so S1 R1 and S2 R2 have they are coprime to each other. So the greatest common divisor between them are 1. Okay? And we claim that if we just need 2 of them, and we can find R with probability at least 1 over 4. Okay? And yeah, so let's go through the number theory here. Okay? So we look through all prime number Q, and okay, so I guess the first sentence is most important. So when does U don't give the don't get the correct answer R? when you take the least common multiplier of R1 and R2. Okay, and so remember R1 and R2 they all come from R. They are this R divided by something get R1 and R divided by something get R2. Okay, and so if the least common multiplier don't go back to R, means that they are divided by something common. Okay, so that's why you take common multiplier, you steal something away from R. Okay, and so there will be some Q that when you go from R to R1, you are also dividing the same factor from S1 prime and S2 prime. That's why you can take the factor from both these upper side and lower side, etc. Okay, so the common factor from R must be also common factor that's the difference between R1 and R and R2 and R must be also on S1 prime and S2 prime. Okay, so the factor Q will divide S1 prime and divide S2 prime. Okay, so this notation here just means that Q is dividing the numbers. Okay. Okay, so we will have a Q that divide everything. You will divide S1 prime, S2 prime, and R. Okay, and so this Q is giving trouble. Okay. Okay, and now let's just look at the probability. So S1 and S1 prime and S2 prime, now remember they are totally we haven't used this I guess let's start with probability. So we here guys the probability is we fix some Q, so we are going to look through the OQ. So this one is for this thing we are like a fixed Q. So if fix a Q and we want to see what's the probability of a given Q that satisfy both those. So we want for Q that will be that will divide S1 prime and divide S2 prime. Okay, and so here Q is something fixed, and the randomness is over S1 prime and S2 prime. Remember, S1 prime and S2 prime are draw over something from 0 to R minus 1. Okay, so random over S1 prime and S2 prime, what's fixed Q, what's the probability that Q divides S1 prime and Q divides S2 prime. Okay, and because S1 prime and S2 prime are independently drawn, so probability is just the product of probability. This is the independence, and then because it's uniform, then you think a little bit about the probability. You see that each probability will be about 1 over Q, but R might not be divisible by Q, so it might be less or equal. Okay. Anyway, so the probability, each of the probability will be about 1 over Q, and so total thing is 1 over Q squared. And I guess here if we are being a bit careful, so we know also Q divided by R. So if you condition on Q divided by R, this will actually be 1 over Q squared, because every because every reminder when you divide by Q will be same probability. Okay, and anyway, so it's about 1 over Q squared here. And then now we just sum over the probability over Q and see its bounded value. Okay, and so we have probability over uniformly random S1 prime and S2 prime, and I guess that's why you don't want to condition on Q. Is condition on Q divided by R is a bit weird. And anyway, so this is less than Q squared, and now we just sum over OQ. Everyone is every Q is 1 over Q squared, and actually even if we sum over O prime is not too much trouble, because this 1 over Q squared decay very fast. Okay, so probability of you having no conflict factor is you get a union bound is 1 minus sum over sum over for any Q. Guess this is no conflict, so I guess this should be a greater equal here. Okay, because you are doing union bound. Okay, so the probability is greater or equal to 1 minus every event that you can get wrong. Okay, so you sum over O prime Q such that Q is a common factor on S1 prime and S2 prime. Okay, and we have bounded this probability. We know the probability is less than 1 over Q squared. And here is another thing on homework. So basically, you try to sum over this thing, and you see that this part is less equal to 3 over 4. So the total probability is greater or equal to 1 over 4. And so this is this summation is actually not too hard, so you don't even need to use prime here. If you just sum OQ from 2 to infinity, this will be a bounded thing, because just 1 over Q squared, you think about the integral is it has a converging tail. So so this thing is bounded, and you get a bounded value here. And we don't actually care about how big or small this value is, as long as it's a constant. Okay, so so probability is at least 1 over 4 here. Okay, so that's order finding. And I guess let's try to run through order finding once again. It's a bit of an example. I think we'll also see this in homework and probably in your final. So so let's see how order finding works out in example of good numbers. So big N equal to 15 and x equal to 7. Okay. And here we choose t that give you nice value already. Okay, so we choose sorry, t is just something, so t is something big enough. T is equal to 11. It has a lot of bits. I think it's more than enough bits, but it's like for just here for showing how it works out. Okay, and here we have all the steps that go through with dirty detail of phase estimation. Okay, so on the first step of phase estimation, and we will make the first register equal superposition over OJ, and J is from 0 to the t minus 1. Okay, and so first register is from 0, 1 to the t minus 1, and the second register will be 1. And then you apply UX condition on first register. Okay. And on the condition on first register, you apply UX to the N. Okay. And so I guess here we have a typo. This should be, this should be, let me see, it should be UX to the J, I think. What do we have? Anyway. We apply UX to the J sub N here. Okay, and so we will keep multiplying different power of x on the second register. So on this 0, the second register is still 1, and on this 1, second register becomes 7, and on this 2, and you will get 7 squared equal to 4, and on 3 you will get so this is 4 times 7 equal to 28, then mod 15, you will get back to 13, etc. And then you see on 4th, so actually r just equal to, so you see r is actually just equal to 4 here, because on the 4th power of 7, you already back to 1, etc. Okay, and with this, and then we do inverse QFT on first register. Then we get 4 different things. Okay, so how should I say? Okay, so we have 4 different eigenvalues. I guess in this form it's not very obvious, but you will get 4 different eigenvectors because r equal to 4. So there will be 4 different eigenvectors being the 4 different being the 4 different combination of these 4 states, because the second register is it will keep repeating this 1, 7, 4, 3, etc. Okay, and with 4 then we have 4 eigenvector here, and the first register will give you the eigenvalue of that. Okay, and the eigenvalue of that will be just and the first register has I think it's actually a bit weird. 2 to the t. I think. Oh, never mind. Yeah. So 2 to the 11 is yeah. So 2 to the 11 is 2048. Okay, and so you will have this is 2 to the 11. And the result of first register will be, so we will have this S over R times 2 to the T. Okay, and we know S over R equal to 4, then S is 0, 1, 2, 3, and yeah, oh sorry, so it's actually down here. Okay, and reading my slides. Anyway, yeah, so we have 2 to the T times S over R. Okay, and 2 to the T is 2 to the 11, and is this 2, 0. I guess I should write it again. It's not down here. 2 to the 11 is 2048, and yeah, and it's 2048, and then it divided by 4, and it's 512. Okay, and yeah, so you have 2 to the T over R equal to this 512, and then you have 0, 1, 2, 3 here. Okay, and yeah, okay. And when you measure the first register, we'll get each of those with equal probability, and so you'll get your random S over R. Okay, and yeah, suppose you get so we want to pick 2 of S over R here, and suppose we are getting a bit lucky, we get this one and this one. And so with 1024 over 2048, you will get this 1 over 2, and 1536 over 2048, you get 3 over 4, and yeah, so you get the least common multiplier between 2 and 4, you get is 4. Okay, so that's order finding with a bit of a number field. Any question? If not, yeah, finally let's actually see factoring. Okay, and now we have nothing to do with content. Now it's totally classical part. We're just talking about number theory here. Okay, so now we talk about the other part about factoring is how to use number theory to use order finding to solve factoring. Okay. And yeah, suppose we have okay, so suppose we have integer n, and we want to, well, this is a factoring problem. We want to find p and q such that p times q equal to n. Okay, and the way we do this is we have order finding. We have can find the order of some x to n, and what we do is we'll just start with random x and do factoring. Okay. And yeah, so so the idea is we want to find some y such that y squared true solution. We want to find some y with y squared equal to 1. Then we can have y minus 1 times okay, so if we have some y such that y squared equal to 1, then we can have y plus 1 times y minus 1 equal to 0 model. Okay, that's kind of the idea. And yeah, but there will be some case where this doesn't work out. So you have y plus 1 times y minus 1 equal to 0 model, and if none of them are 0, then you get 2 non-trivial factor p and q here. Okay, so that's the idea. And to get this is we want to do order finding. So we want we want to have x, and we want to find x to r equal to 1. Okay, So this is the order finding part. Okay, and so we have x to the r equal to 1. Okay, and so here we need to get lucky. We need to have r being an even number. Then if r is an even number, then we can have then x to the r over 2 is it will be our y. Okay, so yeah, so y will be our x to the r over 2. So x to the r equal to 1, then we have x to the r over 2 times x to the r over 2 equal to 1. These are everything is modern, so let's be sloppy with the modern. Okay, and yeah, so we will have x to the r over 2 minus 1 and x to the r over 2 plus 1 equal to 0. And so if we are getting lucky with our number 3, then these two are our factor. Okay, so that's the idea of factoring. And yeah, so really the algorithm now is just keep picking random x that's co-prime to n, and pick until you get lucky with one of them being a factor. With, I guess, if one of them is factor, another one is a factor. Okay, so yeah, so you just keep picking random x until you are lucky you get two factor here. Okay, so the high level idea is pretty simple here. And yeah, so the I guess the rest of the slide are just showing you how to get lucky with your x with a higher probability, and you actually have a high enough probability. Okay, and yeah, so first, so what we do is we pick a random x, so x from 2 to n minus 1. Okay, and so first thing you need to check is x need to be co-prime to n. And actually, if it is not co-prime to n, then you get lucky because you already get a factor of n. Okay, and yeah, so this is the first check. You are co-prime. If you're not co-prime, then you actually already solve your factoring problem. Okay, and yeah, and then the second part is you use order finding. So this is the actual part, quantum part. You use order finding to find the order R of x. Okay, and yeah, if R is odd, then you are unlucky. You just need to try another x. And here is the number 3 part. Number 3 tells you this odd happen with well, some constant probability is a bit harder to get the exact number, but well, anyway, it's a constant. It's something that doesn't scale with it, so it's okay. And yeah, so with enough draw of x, you will get R is even. Okay? And but even when R is even, you still need to get lucky because you need that none of those factors actually equal to 0. You want none of them equal to non-zero. I think. Okay, so we need to look at detail. But the high level idea is one of them 0, then you are a bit screwed. But the actual detail we want to look at here. Okay. So anyway, so we have x to the r over 2 squared equal to 1, and we have this decomposition. This is the starting point, and okay, then now this part is subtle, and so I need to actually read the slide. Okay, and yeah, and yeah, it's a bit subtle, but anyway. Oh, okay. So the cases are a bit more complicated. Okay, so I guess this is not for analysis because I might have more than one fact. Because I think there is a it's there might be something a bit more subtle, but the high level idea is here. Okay, so think about if n is just have two factors p and q. Okay, and then you have two things multiplying together equal to power of n, and so those pq factor can be in 4 different distributions. You can have pq and you can have both PQ on the first on this first component, or PQ on the second component, or one of them P, another than Q, and another than Q, another P. Okay, And this is not totally correct because you can have more powerful PQ because this is zero mod n, so this is n times some number, this is just not n. So in particular, you can have like a PQQ, something like that. Okay, so yeah, but intuitively you can have those things, and so if you have this case is actually something that cannot happen because so by writing this we mean the first factor has both the PQ factor and means x to the r minus x to the r over 2 minus 1 is equal to 0 mod n. Okay, so this one means I guess that's right here. So with this one we have x to the r over 2 minus 1 equal to 0 mod n. And then this is actually something that cannot happen because from here we see x to the r over 2 equal to 1 mod n. And this equation says that r over 2 is I guess order because we say it's order finding. Okay, is order of x, but r is already the order of x. So r is already the smallest number such that x to the r equal to 1. So you can have r over 2 actually also equal to 1. Okay, so this is impossible. Okay, and then the second one is when this this thing has both factor and PQ. And now this is another part you need to deal with number 3 just as you are unlucky. Okay, so when this happen is when this happen, well, this is nothing much you can do. So but it happen with constant probability, and you just try another x. Okay. And then with the other two things, you have a non-trivial solution, and you can find just the GCD of the first factor with n, and yeah, you will find factor p or factor q here. Okay, and yeah, so that's the idea of factoring. So we have a lot of case here. But basically what we are doing is we can just keep drawing x and try to find the GCD x to the r over 2 minus 1 with n and see whether you get a non-trivial factor. Okay, and yeah. I guess this is so this is about a bit of factoring. Okay, so we are talking about so now we are talking about small part of a factoring algorithm, and the next slide is we are trying to find this GCD. Okay, so keep saying that we can find we want to find the greatest common divisor between two numbers, and want this to be done efficiently, and this is something I think we learned in elementary school, but still see this once again. Okay, and I think maybe if I say this in Chinese, some of you will be more familiar with this. So this is called 占准相除法. Okay, and yeah, so you just keep dividing the two numbers with each other, and you'll get the greatest common divisor. So it's so you have 210 and 45, and you divide 210 with 45. You get this 4. We don't care about this 4, but we get a remainder being 30. And then we take this 45 and 30 and divide each other. You get a remainder being this 15. And yeah, you keep this division. And yeah, and then you see the 15 is the thing that divides everything. And the greatest common divisor is this 15. Okay, so this just shows you that finding GCD can be done very efficiently. And yeah, so if you actually calculate try to bound a little bit of how efficient you can do this, you see that you just need to, you can do this with, I think, a linear time in the number of bits here. Okay, so this is order L in terms of how big L being log n. Okay, and now here is a bit of a theorem, and I think This is a bit of a tricky part. Okay, so this is a theorem bounding that what's the probability of all your number series constant probability happening out. And yeah, I never check out the detail, but I know it's a constant, but I keep seeing different constant on different source. Okay, so it's a bit tricky here. But anyway, I think the constant of everything workout. So here is the constant of everything workout is should be at least 3/4. But sometimes I also see 3/8, so I'm not very sure. But it's a constant. Okay. And yeah, so here is yeah, just a theorem to a bit more detail. So you have n, and yeah, so we say we have some n here, and it has m different prime factors, and m different prime factors, and then you draw uniformly random x, and then we want it to be everything good happens, so we want the order to be even, and also x to the over 2 doesn't equal to -1, so this doesn't happen, so both of these happen. Then so this theorem we copy from book says that it's at least 1 minus 1 over 2 to the n. Okay, and m is at least 2 here, so this probability is at least 3/4. Okay, because and so here we see that you have more factor, then the probability gets even bigger, etc. Okay, and yeah, yeah. So x is uniform random and also coprime to n. Okay, and anyway, so that's a theorem that we do prove. This is total number theory, and but the book actually approved in I think in appendix. So if you want to see the proof, you can check the New Central. So proof book. Okay. And yeah, so that's really about factoring, and I think in the test next 10 minutes we can show a bit of I think it's a bit boring, but yeah, but so here is the procedure of the whole factoring algorithm. So basically, here yeah, I guess that's a bit of detail. Okay, so yeah, so first you need to check who is yeah, first you need to check that 2 is not your factor, and well, it's easy to check. Okay. And if 2 is not your factor, then you want to, so I guess to use this theorem, you want to have more than one factor. So you want your n not to be just 1 prime to some power. Okay, and you can check this by just keep taking the roots of n, and there are not too many things to check. You just check square root of n, cubic root of n, etc. Okay, and yeah, because you want this factor to be at least 2 or at least 3, so there are not too many checks you need to do here. Okay, and so here are just setup. Okay, and after the setup, then now we start doing our choosing random x and finding the order of x. Okay. And yeah, then we just need to get lucky if r is even and x to the over 2 doesn't equal to -1, and we can just compute GCT of x to the over 2 -1 n, and yeah, so then we get a factor here. Okay, and oh, a bit forgetting why do we need n odd. I think probably here we need also n is odd. So we want to bound the things, we need n is odd here, and that is why we want to check n is odd on the first step, and it's really quick. Okay, so that's factoring, and I guess we can run through an example. And let's just kind of see the number series actually work out. So n equal to 15 and x equal to 7. So this is the example we run before. And already see I equal to 4 here. and x to the r divided by 2 is x to the 2. So it's 7 square, and it's 7 square is 49, and 45 mod 15 equal to 4. And 4 don't equal to 1 mod 7 mod n, and so we should be good. Okay. And so what we do is we take this x to the r over 2, so this 7 square, and minus 1, so it's actually 48 now. And we have GCD of 48 and 15, it becomes 5. Sorry, this is wrong, right? GCD of 15, 48 and 15 is not 5, it's 3 here. And yeah, but anyway, we got another factor, so it works. So n is 15 equal to 3 times 5. Okay. And yeah, so that's how it works. And I guess let's check the other part that actually work here. So GCD of, so instead of minus 1, we can take the plus 1, it should actually get a factor x to the r over 2, r over 2, r over 2 plus 1 and n, and this should be GCD of 50 and 15, and this should give you this 5 here. Okay, so yeah, that's the Shor's algorithm. Okay, and I guess do we have time to say this? It's a bit weird. Yeah, we have 5 minutes. Let's try to cram this through. Okay, so I guess a bit of history. So we said that phase estimation is actually discovered by Kitaev. Okay, and so the phase estimation view of Shor's algorithm is actually developed by Kitaev instead of Peter Shor. Okay, so how does Peter Shor actually come up with Shor's algorithm is think in this way. Okay. And so we break Shor's algorithm up, and we think about what the second step, the side 2 here. This is actually something we said before. Okay, think about what side 2 here. Side 2 is just sum over. You have equal superposition of k here or j here, and on the second register you have the summation of all those x to the r, power of x here, right? And yeah, so you can have a different way to do your UX, but at some point you will get this side 2. Okay. And yeah, and the idea of Peter Shor is well, we can get this side 2 here is equal superposition of all those obvious state of x, and then we just do something like in Simon's algorithm. Simon's algorithm, we say we do this query and we just measure a second register. Okay. And so what do we think about we measure a second register here? And so this doesn't change the algorithm at all, because by the principle of I think forgot the name, but the principle of you can measure everything. Okay, yeah, and because this register doesn't affect the output, you can just measure it, and if you measure it, then you will get one of those power of x, right? So you get x to the some power as second register, and on the first register, okay, on the first register, so say you get x to the k here. This k is something from yeah, we should say here, right? K is something from 0 to r minus 1. Is about uniformly random, it will be a little different, but about uniformly random if you make your t big enough. Okay, so this is approximately about, okay, about the uniformly random k, and yeah, and what do you get on first register? No, it's interesting. So you get all those j here, such that you will get x to the k on the lower end here. So it's a k, and then you add r different. You add r here, you get the same x to the k, etc. So you get a k, x plus r, and sorry, k plus r, k plus 2r, etc. Okay, so you get all those computational basis data spaced out with r. Okay, so yeah, and this thing. Okay, and so this idea is similar to Simon's algorithm, where you measure the function value and you project onto all the things that give you the same function value. Okay, And then from here, then that's why Peter should want to do Fourier transform, because you get some periodic function here. Then from classical Fourier transform, you know that you get basically a periodic function. You do Fourier transform, you can find its period. Okay, and yeah, so that's the idea. Yeah, and so yeah, so if you yeah, so the idea is that you get all those k plus r, etc. And you do and yeah, so this function is actually some very famous function. It's called impulse train, and we know that you do Fourier transform, you also get impulse train. And when spacing is r here, the spacing will become 1 over r. Okay. And so why we want to change spacing from r to 1 over r is because the original impulse train here, we have random displacement k here. Okay, and yeah, this k will prevent you from yeah, this k will prevent you from learning r, because you get k plus r, you get k plus, if you just measure this, you get k plus some r. You don't know, because you don't know k, you don't know r. Okay, but when you do Fourier transform, then actually the start point becomes 0, and this k becomes some phase on all those things. And when you measure, then you get your uniformly random s over r, and that's why you can get 1 over r. Okay, and yeah, that's it. And next time, yeah, maybe we'll talk about this view a little. Be more detail on next time, and I think next time we'll also start our global algorithm. Okay, yeah. So see you on Thursday. Sorry for going over time a little bit.